Oh, okay. So now, whether my voice is audible now? Okay, so there was the technical problem my side. Oh, I'm sorry for that. So let me revise the question quickly. So I think the steps are clear to you because it's nothing but it's only asking you to find out whether the divergence theorem is valid inside this volume V. Okay, so for this one, we have a volume like this. So started for so you have a half of the hemisphere and some of the volume, a conical part has been cut out from this hemisphere, and you have a function V like this. Okay. So V it is given in terms of the spherical coordinate system. So divergence theorem, if you recall, it's a it relates the volume integration with the surface integration. And if you recall the general formula for for finding out the divergence, you have seen this formula. So I have just written this formula to let you recall what was the formula for finding the divergence. Okay. So and you know for this spherical coordinate system, you have HI, SJ, and HK. This is 1R and R sine theta. So divergence of F, if you calculate it, just put the value of VR, V theta, and V phi. So you will see it will come out as 3 cos phi plus 2 cos square theta sine square theta and cos phi sine theta. Okay. Okay, let me ask one thing. If you are not able to hear my voice, whether this my iPad it was visible or not, or it was also not visible. Whatever I was writing, it was not visible at that time. Okay, so it was not visible. Okay. Okay, so okay, if it is like that, so if you have any doubts in any of this step, let me know. I think these are easy to trace the problem, the steps. But if you have any doubts, let me know, and then I will let you clarify your doubts, and we'll start solving next problems. Okay. So what I've done is, yeah, I will save the slides by tomorrow. Uh, both the third and I think second and third and fourth I will share you by tomorrow. Okay. So don't worry. So what I have done is, so I have calculated what is the divergence of V. And from that, I have seen instead of calculating the whole integration, I was checking whether any of this integration is, whether we are getting any zero for this integration or not. And if you see, there is a cos phi term here, and integration of cos phi from 0 to 2 pi, it will give a zero value. So that is why whichever term is cos phi term, this we are not going to calculate it because it's already zero. So this term and this term will vanish. And only the second term will remain. Okay. So this is 2 cos square theta minus sin square theta. And so you have the whole integration this and just put the value of theta and theta 2. You will get the divergence of the left hand side of this divergence theorem will come out as minus root 3 pi r cube by 12. And for the surface integration, you need to see what are the different type of surface we have for this case. So here we have three types of surface. One is the bottom circular surface, and one is the outer spherical surface, and one is the inner conical surface. So for these three type of surface, you need to calculate what will be the surface integration. Okay. So for this, what I've done, so to find out what is the dA for this three type of surface, I have checked which one of the following is constant here and which two of this parameter is variable. So if you see the circular surface, for this theta is pi by 2. So the theta will be 0. Only the r phi term will contribute to the area element. So that is why the dA will be r dr d phi theta k. Okay. And if you see the theta, so V dot dA will take the term from V, which is theta k. And if you see V theta, this is R cos theta sin theta. And for this surface, theta is pi by 2. So that is why the integration will be 0. So for first term, this integration is 0. For the second surface, where we have a surface like this, the spherical surface, the outer spherical surface, theta will vary from pi by 6 to pi by 2, and phi will vary from 0 to 2 pi. So that is why dA element, it will be r square sin theta d theta d phi in the r cap direction. And for this surface, outer surface, r is not a variable, it is constant. So, and if you take the dot product of V with dA, so this will give this term. And if you check the integration, it will come out as 0. So I am letting you to find out whether the integration is 0 or not. So just check once, because it also have cos phi term. If you check, so cos phi from 0 to 2 pi, it will give a 0. So it should be 0. And for the third surface, theta is pi by 6. Theta is constant. Theta is not varying. So that means the area element will be in the theta cube direction. So dA will be minus r sin theta dr d phi theta cube. So I'm taking minus theta because if you see the spherical coordinate system, the theta is in this direction, right? In the downward direction. But for this surface, theta cap will be in this direction. So that is why I have taken minus theta cap for this case. And theta is already pi by 6. So if you put it, it will come r by 2 dr d phi theta cap. So, VDA, it will be minus r cos theta sin theta r by 2 dr d phi at theta pi by 6. Just put the value and find out the integration. So just put the value because you know VDA. So, and you know what is the variable. R will be from 0 to R. Pi is from 0 to 2 pi. So if you put it, this will come out as minus root 3 pi R cube by 12. Okay. So this is equivalent to what we have seen in the left hand side. So that means for this surface, the divergence theorem is valid. Okay. So this is all about the week 3 contents. Now we'll see solve few problems that is related to week 4, which is solving the problems related to electrostatics. Okay. So what do you mean by electrostatics? So electrostatics means when we are considering the source charge is at rest and the test charge is it can be in rest or it can be moving. But for electrostatic condition to be valid, the source charge should be at rest. Okay, so this is what you mean by electrostatics. So let us solve our first problem. So this is related to the uh, field produced by a linear charge density lambda. Go through the question once. Please read the question once, then I will show the steps that you can follow to find out the answer, or you can also solve side by side to check whether the answer is correct or not. Okay. So the question says a semi-infinite line, it's charged with a linear charge density lambda. Determine the magnitude and direction of the electric field lying at a distance d from the line. So you need to calculate the field here due to the semi-infinite. So it's not a finite rod, it's a semi-infinite. So for this one, what is the usual procedure? So first you need to take a small area element, small charge element. So from the origin. So let us say in x distance, you have a small charge element dx. So because of this charge element, you will have a electric field at the point here. So we are calculating the field at the point B. So this will produce a electric field dE, right? Let us say this is R, this is D. So R is nothing but D minus X, which is dJk minus Xik. So always take the coordinate in terms of the right hand one. Always take the right hand coordinate system because it's mostly used. Left hand coordinate system, it's also you can use it also, but we are not using it. We are just sticking to the right hand coordinate system. So for this, what will be the DE here? Electric field will be K. K is nothing but 1 by 4 pi epsilon naught. K dq rq r vector. Okay. Mm. So you have K dq will be lambda dx and rq will be square root d square plus x square, and r vector is nothing but djk minus xik. Right? So you need to do the integration now. So E will be integration of dE, which is dk lambda dx jk by d square x square e by 2 from 0 to infinity minus k lambda 0 to infinity x dx ik d square plus x square 3 by 2. So I think these two integration, you know how to do it, right? For this one, you just need to do a trigonometric substitution for the A part. And for the B part, what you can do, you can take this whole term as a some t square. Okay, so whenever you have x dx by d square plus x square 3 by 2, you can take this as t square so that you can easily calculate what will be the integration value. For a, if you see the figure, so let me take this as theta. So tan theta will be x by d. So x is d tan theta. Okay. So you have dk. So let us just calculate dx d square plus x square 3 by 2. So x is d tan theta. So dx you can calculate, it will be d sec square theta d theta. So if you put it, it will come out as 1 by d square cos theta d theta. So I'm not going into the details of this substitution. Just check whether you are getting the terms or no. So this will be 1 by d square sin theta d theta. Sorry, sin theta, which will be, so we need to put the value of theta now. So when x is 0, then theta will be 0. So theta is 0 and x is infinity. Theta will be pi by 2. So that is why it will be 0 to pi by 2. So 1 by d square. This is for the b part. So a, it will come out as dk lambda by d square jk, which is k lambda by d jk. For b, you have 0 to infinity x dx d square plus x square 3 by 2. So just put this as t square. So this will be dt, t dt, and you will get, this will come out as minus 1 by t, or 1 by t is nothing but square root d square plus x square, 0 to infinity. So this will give value of 1 by t. So for B, you have electric field k lambda by d ik. So that means the electric field will be A plus B, which is k lambda by d ik minus k lambda by d jk. Okay. So in x and y direction, you have same electric field. So that means if you need to calculate what will be the magnitude, it will be nothing but square root of 2 k lambda by d. And the angle between this ex and ey, it will be 45. Okay. Okay. So let us see our second problem. So I want you to solve it. Let me know the answer. So the question is about which one of the following vector field represents an electrostatic field. There are four options. One is xik, 2yz plus 3xz k. Second is xyik minus 2yz plus 3xz k. Third one is x square ik plus z square jk plus 2yz and the fourth one is none of this. So calculate it and let me know the answer. You can see it here for A and B. The options are quite similar. The representation of the field. Only the sign here is plus and the sign here is minus. So if you can calculate for this, the answer will be same for this also. So you just need to check whether this one is satisfying or this one is satisfying, or neither of this is satisfying the electrostatic condition. Anyone? Yes, option C is correct. So these two options, they are not a electrostatic field. Okay. So the condition you need to check is whether the curl of E, whether this is zero or not. If it is zero, then it's the electrostatic field. If it is not zero, then it's not a electrostatic field. And if you check for this case, it will come out as zero. So just check whether the curl is zero or not. Curl for the Cartesian one, it's easy. Dou x, dou y, dou z, ex, ey is. So this will be I cap dou y ez minus dou z ey minus j cap dou x ez minus dou z ex plus k cap dou x ey minus dou y ex. And if you put the value of ex, ey, and ez, you can check where this will give a zero value. Okay, so let us move to our next problem. So the question says there are three positive charges. Three positive charges Q are placed at the vertices of equilateral triangle of side A. And another point charge minus Q is placed at the centroid of the triangle. And if the force on each of this charge Q vanishes, then find out the ratio of Q by Q. small capital Q by small q. So let me draw the charge configuration. So you have a charge like this. There are three charges here, and there is a charge minus q at the centroid of this equilateral triangle. So that means if you draw and you need to find out what is the ratio of capital Q by small q. For this, what you can do, just check which of these forces are cancelling with each other. So for this point charge, it's given the force on each point charge is 0. So let us see for this second charge, this Q, this will give a repulsive force, F1. This will give a repulsive force, F2. But the minus Q will give a attractive force, F3. And to balance to make the force on charge small q is to 0, that means this force will sum up to 0. So F1, F2 plus F3 is 0, right? So instead of calculating F1, F2 and F3, let us see the components. So F1 is in the y direction, F2 making this will be theta 1. So x in y direction you have, or in x direction, let us say, this is F1 cos theta 1. In y direction, this is F2 sin theta 1. For F3, let us say this angle is theta 2. So, or instead of this, you should take this angle. So, theta 2. So, this in x direction, you have, sorry, y direction, you have F3 cos theta 3. And in x direction, you have F3 sin theta 3. So this F1, F2 will cancel with F3 sin theta, and F2 sin theta 1 will cancel with F3 cos theta 3. So instead of cancelling the x term, so you can see for y you have two, you need to calculate only two. So better take the y term to get the answer quickly. So that means F2 sin theta 1 should cancel F3 cos theta 3. And you can see the distance between Q and Q is A, and the distance between Q and minus Q, this is this length, which will be A by root 3. Okay. And theta 1, theta 2, you can easily guess theta 1 will be 60 degree and theta 2 will be also 60 degree. So you have F2 sin 60 into F3 cos 60. This will give, to constant term will cancel. This is Q square, R2 square, and cos 60 is root 3 by 2. And F3 is Q by R3 square, and cos 60 is half. So you have this also cancel this. Q by Q is R3 by R2 whole square multiplied by root 3. This R3 is A by root 3 and R2 is A. You can easily check, this will come out as 1 by root 3. Okay, so the answer will be option B. So this is how you can minimize the calculation steps. Okay, so just see which one of the path is taking the minimal calculation to do. From that, you can easily guess the answer for the question. So I hope this problem is clear. Let us move to our next problem. So next problem says you need to calculate the electric field at a distance z above the center of a rectangular loop, which is a side A and B. And this rectangle has a linear charge density of lambda. If you see Griffith, there was a problem which it's similar to this, but it's a square loop. Instead of a rectangular loop, the question asks about calculate the electric field for this square loop. But for this, we have a rectangular loop. But if you can calculate what will be the field for a rectangular loop, it's easy to calculate what will be the field for a square loop, because for rectangle A is not equal to B, and for square A will be equal to B. Okay, so that is why I've taken this problem, so that it will be a general case and you can easily follow up the steps, follow up the procedure, what will be the procedure for the square loop. Okay, so let us first take a small area element. So your first task is to take a small area element and find out what will be the D. This is Z. Let us say we are checking the B part in the, let us say this in Y direction, we have a dy, and this dy length element, it is producing a field de here. This length will be a by 2, and let us take this will be r prime, and this is r. Z is this perpendicular distance. So from the figure, you can say r is nothing but z minus r prime. And from this triangle, you can say r prime will be a by 2 I cap plus y j cap. So that means r is nothing but z k cap minus a by 2 I cap plus, sorry, this will be minus y j cap. So d will be dq r 4 pi epsilon naught r cube, which is for the linear charge density you have, this will be k. K is 1 by 4 pi epsilon lambda dy. R is zkk minus a by 2 ik minus yjk, whole divided by z square plus a by 2 square plus y square. And you can check it here also for this, for the I and j part. This will cancel. This when you take the integration, this will give a zero value because for area element here dy, you also have a area element here also for this length. So this length is similar to this length. So for this area element, this will be plus a by 2 I cap and plus yj cap. So that is why when you sum up the field for this and this I cap and j cap will cancel because of the symmetry. Only the j cap component will remain. So that is why we won't consider this two part. So the dE net will be 2 k lambda dy z cap z square plus a by 2 square plus y square 3 by 2. And a will the integration from minus b by 2 to b by 2, right? Length is from minus b by 2 to b by 2. So this will be 2k lambda z k cap minus b by 2 to b by 2 dy z square plus a by 2 square plus y square 3 by 2. So now to solve this, you can make a substitution for the y variable in terms of this constant. So if you take y is, let us say y is square root z square plus a by 2 square tan theta. Let us take this. So we'll eventually eventually substitute theta in terms of y. Okay. So dy is, this is constant z square a by 2 square sec square theta. So we have E1 now, or the field 2k lambda z k cap, and dy is, just make the substitution. This will give square root z square a by 2 square sec square theta, and for the this part you will have z square a by 2 square 3 by 2 sec q theta. So y square will give a z square plus a by 2 square term, and you can take it out from this summation. So that is why you will have a 3 by 2 here and sec q theta. So this will cancel. You have now is 2k lambda z k cap. So this is half and this is 3 by 2. So we'll get z square plus a by 2 square. And there is a cos theta term. Cos theta integration will give a sin theta, right? And we don't know the theta limit also. So for this, what we can do the back substitution. We will convert theta to y because the y integration we know. So that is why we'll go back to the y term. So we've taken tan theta as y by square root z square plus a by 2 square. So from this you can easily calculate sin theta, right? So sin theta will be, this will give y by square root p square plus b square, which is y square plus z square plus a by 2 square. So this is 2k lambda z k cap z square plus a by 2 square y square plus z square a by 2 square. And the y limit is from minus b by 2 to b by 2. Just put the limit, you will get the first, the electric field due to this two part of this rectangular loop. This will be 2k lambda z b z square plus a by 2 square z square plus a by 2 square plus b by 2 square. Okay, so this is for this two part which is length element B. Similar process, you can follow the similar process for the B part or A part also. For this two part, the process will be same. So let me just briefly go through this. For this two part, what you can do, just take a length element. Let us say in x direction, you have a dx length here. And because of this dx, you are seeing an electric field in the here as dE. This is R, this is R prime, and this is A by 2. Not A by 2, this will be B by 2, right? This is B by 2. So dE2, R will be ZK cap. Similar to the previous step, it will be ZK cap minus R prime and ZK cap minus B by 2 J cap minus XI cap. And similarly, for any length element here, you also have a length element here which will cancel this I cap and J cap component. So that is why we won't include this two part, only the Z part will include. So dE2 net will be 2Z k lambda dx k cap by Z square plus B by 2 square plus X square 3 by 2. And the integration limit, the X will vary from minus A by 2 to A by 2. Just follow the same process. Make the substitution of X in terms of Z square plus B square. And if you do it, you will get E2 will be 2k lambda Z A Z square plus B by 2 square plus B by 2 square. Okay. So you have E1 for this two part, and you have E2, sorry, E1 for this two part and E2 for this length. So the net electric field will be E1 plus E2. Okay. So E will be E1 plus E2. And for the square loop, you just need to put A equal to B. Then you can easily check whether the answer is similar to what the solution that is given in the Griffith. Okay, so is this problem clear to you? Or do you have any query in this problem? If this is clear, then let us go Solve question number 5. So there are 4 positive point charges. Q placed at 00101101 on the xy plane. The magnitude of the electrostatic force experienced by each point charge is. This is this I think it's easy to find out the answer. So let us quickly go through the solution. So R1 is given, it is 00, R2 is given, it is 10, R3 is 11, and R4 is 01. So the force, all the four charges has same charge Q. So force on 1 due to 2, you can write it as Q1, Q2, which is Q square 4 pi epsilon K R12 by R12 cube. So R12 will give I cap, right? So this is K Q square I cap, and mod of R12 is 1. So this will be not, this will be 1. So this is KQ square. And F13 will be KQ square F13 F, sorry, this will be R R13 R13 cube. R1, R3 are known. So R13 will be IK plus JK. So this will be KQ square IK plus JK. And mod of IK plus JK is root 2. So this will be 2 root 2. Similarly, F14, this is KQ square R14 R14. So 1 is 0001. So this will give JK. So this is KQ square JK. So the force, total force will be summation of this force, these 3 forces. So F total will be KQ square IK plus JK plus IK plus JK by root B. Magnitude you can easily find out, right? You know F. So this will be come out as Q square by 4 pi epsilon naught 2 root 2 plus 1 by 2. And if you check it, the answer will be option A. Okay. Okay, question number 6, it's quite easy. You just need to find out what will be the total charge in a cube. So it's given a cube is defined by x from 0 to a, y from 0 to a, and z from 0 to a. And the charge density is varying is rho 0 x by a. So for this, you need to calculate what is the total charge q on this cube. So please calculate it and let me know the answer. Rho 0 is constant, only x is the variable. So option B. Yes, you are correct. So answer will be option B. So what were the steps? Q is nothing but rho dV. And for a cube, it is dx, dy, dz. So, and rho is given rho naught x by a. So this is rho naught by a x dx, dy, and dz. So 0 to a, 0 to a, 0 to a. 1a will cancel with this. So this will give a square by 2 and a. So rho naught aq by 2. Answer will be option B. Okay. Then solve question number 7. Given there are 3-point charges lying on x-axis, Q1 is at the origin, Q2 is at x equal to 1 meter, Q0 is at x and x is greater than 1 meter. And the question is to calculate electric force on Q0 due to the other charges. And it's given Q1 is 5 coulomb, Q2 is minus 10 coulomb, Q0 is 15 coulomb, and X is 2 meter. So the answer, I think you know the process because similar to what we have seen in the previous problem. So you just need to see the net force on option C. Yes, answer is correct. You will get option C. So the question was to calculate force on Q0. So because this is negative, this will be attractive and this will be a repulsive force. So these are opposite. This will be minus I cap direction. This will be in the I cap direction. So net force will be F01 plus F02. So this is K, Q0, Q1, and this will be 2 square I cap minus K, Q0, Q2, I cap 1, which will come out as minus 131.25. Okay. Okay, so let us move to our next problem. It's based on a circular loop. So the question says find the electric field at a distance z above the center of a circular loop of radius r, and it carries a uniform line charge density of lambda. This is easy to solve because the main steps that you need to follow is take a small area element, small charge element, and find out what will be the D for this case, and check whether this this electric field has any symmetry or not. If yes, ignore that components which has symmetry, and from that you can calculate the net electric. So for this circular loop, you can, this is R, radius R, which is always constant. Let us take this is dr, not dr, this will be dq. The charge is dq here, and because of this charge at a distance z, will have a electric field d. Let us take this is theta. This is r, this is z. Let us take this is so from the figure you can say uh, r is z minus r. So d will be a dq rq r. Dq is lambda dl, right? So lambda r d theta, right? R is constant. R is z kk minus r rk. And rq will be z square plus r square 3 by 2. And you can see here r cap component. So this r vector, this component has symmetry because for any element here you have a opposite element here. This will cancel the r cap component, so that is why this integration will give a zero value. So dE net will be k dq z square plus r square 3 by 2 kk. So E net will be integration of dE net. This is k z k cap z square plus r square 3 by 2 integration of dq. So kz k cap z square plus r square 3 by 2. Integration of dq will give lambda dl. DL is, as I said, this is R d phi, right? And phi is from 0 to 2 pi. So that is why this will be 2 pi R. We are taking R is smaller. So we have the electric field now, which will be 1 by 4 pi epsilon naught lambda 2 pi R Z k k by R square plus Z square 3 by 2. So this is for the ring. Is the problem clear to you? Okay. So let us move to our next problem. So it is similar to what we have seen in question number 8, but instead of a ring, now we have a disk here. So we have a disk, the distance is z above the center of a flat circular disk of radius r, and it has a uniform surface charge density of sigma. So for this, the radius r is also a variable. So instead of a phi integration, we also have a r integration here. Process is similar. This is the point z where we need to find out the field. So from the origin, we need to take a small length element which will have charge dq. And for this dq charge, we need to find out the field here at a distance r. This will be r, let us say. So dE, it will be k dq by rq, r vector. And as we have seen before, the r cap component, this will cancel because this has a symmetry in this circular disk. So that is why only the z component will survive and will give a non-zero integration. This kz dq k cap rq is similar to what we have seen in the previous question. This is z square r square 3 by 2. And dq will be sigma dA, right? Sigma dA will be r dr d phi. So dE net will be kz sigma integration of r dr z square plus r square 3 by 2 integration of d phi from 0 to 2 pi kk. I think this is what we have seen before also. You just need to take z square plus r square is some variable t square, and from that just make the substitution to find out the answer. And this will give a 2 pi term. So this will be kz sigma 2 pi, and we have minus 1 by t, which is square root r square plus z square. And r is from 0 to r. So now we know the answer. Kz 2 pi will cancel 1 by 4 pi. So this will give 2 epsilon naught, and kk, when r is 0, it will give 1 by z, and r is r, it will give square root r square plus Z square. So this is the electric field due to a disk. You can see the steps are quite similar and quite easy also. If you know how to follow up the step, then you can easily calculate what will be the electric field. So this is the one of the method of calculating the electric field. And if you follow the Gauss law, then it's easy to find out the answer from there instead of following the same this process. But Gauss law is only valid. You can only take Gauss law whenever there is a symmetry. If there is a symmetry, then you can easily calculate the electric field using the Gauss law. Okay. So if there is no symmetry, then it's best to follow up the steps using this procedure. Okay. We'll see how we can calculate using the Gauss law. But for now, we'll stick to the conventional method of finding the electric field. Okay, so let us see our 10th question. It's based on a cylinder. So it's asking you to find the electric field D above a cylinder of radius R and height H and the volume charge density rho and ignore the age. So there is a cylinder. This says radius R, height H, and the distance is this is D. It is asking you to find out the field here at the point P. Let's say this point is P. So I will show you two methods how you can calculate the field for this problem. Okay. One is the taking the area, sorry, so taking a small charge element, then finding out the DE, then finding out whether this has any symmetry or not, and taking the integration. The other method is finding out using one of the shortest route. It's like if you know what is the electric field due to a disk. So cylinder is nothing but it's a combination of multiple disks. So when you merge disks of height h, then you will get a cylinder, right? So in previous problem, what we have calculated the electric field due to a disk. So we can use that answer to get the solution for this problem. Okay. So if you see, we have calculated the disk electric field is this one. Now we'll make use of this electric field expression to find out the field. So for method 1, you have a electric field for the disk. This is sigma z by 2 epsilon naught k cap 1 by z minus 1 by square root r square plus z square. But one thing you can notice is we don't have sigma here. We have rho here. For the cylinder, we have rho. So for that, what you need to do, you have to relate sigma with rho. So for that, what we can do, for any kind of small charge element, the charge will be same, right? The total charge will be same, or dq for the sigma case and dq for the rho case, it will be same. So that is why you can take rho dV for the cylinder is equal to sigma d. We are considering the same charge element for taking the cylinder as well as the disk. So this is dV will be r square dr, sorry, not r square, it will be r dr d phi dz, right? And dA will be r d phi dr. So this will cancel. So that means sigma is related to rho as sigma is rho dz. Now we'll substitute it here. So E1 is rho z dz k cap by 2 epsilon naught 1 by z by 1 by square root r square plus z square. This is for one disk, right? And to find out the total electric field, you have to make a integration so that a disk of height h will merge to form a cylinder. So the variable here is dz, which varies from 0 to h. Okay, so we'll rewrite it. This is, so it's better to take d now. So this is rho kk 2 epsilon naught dz, and integration is from, we'll see the integration limit. First, let me write out the terms. Okay. So z, it will vary from, so when h is 0, the distance between P and the disk will be d, right? And when h is non-zero, which is equal to s, the distance between the disk and the point P is d plus h. So that is why the integration limit is from d to d plus h. Don't take 0 to h. Okay. So this is rho k cube to epsilon naught integration of dz, which will give h minus, here, sorry, there is a z missing here. So you have z dz by square root r square plus z square. So this will give t to power half. So if you take this is as t r square plus z square is t. So dt will be nothing but 2z dz. So check this. This will give a value of half dt by t half. So rho k cube by 2 epsilon naught h minus t to power half. So let us back substitute the t value. T is nothing but square root r square plus z square. Limit is from d to d plus h. So the electric field now will be rho kk by 2 epsilon naught h plus square root r square plus d square minus square root r square plus d square plus, so d plus h, right? So d plus h square. This is the electric field due to a cylinder of charge density rho at a distance d. So this is one of the shortest way to find out the field. But for this, what we have to check, we have to know, either you know what is the final expression of electric field, or one thing you can do, just take a disk, find out the electric field due to that disk at a distance z, then use that and take the integration of h. The second method is our usual method, like just take a small area element and find out the field due to this small area element. Okay, so I will not go into the details, but let me show you the steps. Mm, Let us take, there is a area element here, and the distance from the, this is at a distance, this z, this is r, and let us say for this you need to find out the field here, which is this is r. What will be this distance? This will be mm, h minus z plus d, right? This is this distance is z. So this will be the remaining distance will be h minus z, and we have a additional distance d. So that is why this is h plus d minus z. So d will be, and remember the symmetry element will cancel with each other. So only we have a component in k cube direction. So that is why we'll take the final value. So k dq by rq, r vector, and r vector you can see this is nothing but h plus d minus z minus r, and this part will not contribute to the integration. So we have k dq s plus d minus z k cap over square root, sorry, cube root r square plus d plus h minus z. dq will be sigma dv. So k, sorry, rho dv, right? So rho dv is r dr d phi dz, d plus h minus z k cap r square plus d plus h minus z square 3 by 2. So now we just need to take the, so d phi integration will give 2 pi. So we'll get rho k cap by 2 epsilon naught, and the z integration will be from 0 to h, and r integration is from 0 to r, right? d plus h minus z r dr r square plus d plus h minus z square 3 by. So just take this whole value as some t square and do the substitution. If you do it, what you will get is this will come out as rho kk by 2 epsilon naught minus 1 by square root r square plus d plus h minus z square, and r is from 0 to, okay, and there is a d plus h minus z term here. So finally just check is just putting the limits and multiplying d plus h minus z. You will eventually get the electric field that we have seen before. So this will be rho kk by 2 epsilon naught h plus square root r square plus d square minus square root r square plus d plus h square. Okay, so this is the other method of finding the electric field. So is this problem clear? If not, let me know your query, then we'll solve the next problem. So the next problem is, let me go through the next problem in between. There is an electric field in some region, which is given by E is A R K plus B sine theta cos phi I cap whole divided by R. A, B are constant, and it is asking you to find out what will be the volume charge density, which is rho. Calculate it and let me see whether you are able to calculate. So which one of the following formula I will take to find the answer for this? You know electric field and you need to find out the volume charge density. Which formula relates electric field with the volume charge density? Anyone? Yes, Gauss line differential form. So you can take that and find out the answer for this solution. Okay. So E is no unit use. Divergence of E is rho by epsilon. So rho is epsilon naught divergence of E. And this is given in terms of spherical coordinate system. So just to use the formula, divergence formula for the spherical coordinate. So this will be epsilon naught 1 dou by dou r of r square er plus 1 by r sin theta dou by dou phi of e phi. Er and e phi is given. Er is a by r and e phi is b sin theta cos phi by r. Use this and let me write the final expression. This will come out as a minus b sin phi by r square. Okay, to epsilon. Okay, let us see our next problem. It's also similar to what we have seen in question number 11. Instead of a electric field, now we have a charge current density J, and it is asking you to find out the charge density. And four options are given. So calculate it and let me know the answer. J is given, it is xt I cap minus y square t square j cap. So you need to calculate what will be rho. Option C. No, the answer is option D. I think you have swapped this t square with tq because these are somewhat similar, only the t square is here and tq is here. Yes, option D. So, starting point is the continuity equation. Divergence of J is minus of dou rho by dou t. So, divergence of J in Cartesian coordinate, you have dou by dou x, jx plus dou by dou y, jy. Z component is not given, so let us keep it dou rho by dou t. And dou x, dou by dou x of x, xt will give t plus this will give minus 2y t. Now you need to take the integration. So if you take the integration, rho will come out as minus t square by 2 plus 2y t cube by 3. Okay, so answer is option D. Let us quickly move to our next problem. So question is, a charge q is distributed uniformly over the surface of a spherical cell. So whenever there is a spherical cell, it's like a hollow sphere. Okay. So if it is not mentioned, it's a hollow sphere, but it's mentioned as a spherical cell, take it as a hollow sphere. So there is a spherical surface of radius A centered on the origin of spherical polar coordinate, and the electric charge density rho can be expressed as, there are four options in terms of Q. So calculate it and let me see whether you are able to solve this problem or not. Option C. Yes, it's correct. Okay. So then you know how to calculate it. So it's nothing but relating rho with Q. So you can see here it's expressed in terms of rho is some alpha times delta R minus A. And you know that Q is integration of rho dA. Okay. Don't take dV because it's a spherical surface. In the rho may be confusing here, but this will be dA. So rho is alpha delta R prime A. And dA for this spherical surface is R square, R prime square, sin theta, d theta, d phi. So this will give R prime is nothing but A. The spherical surface charge is distributed here. So it's directly A square. So alpha, and this will give 4 pi, 4 pi A square, delta R minus A. So that means alpha is now Q by 4 pi A square, delta R minus A. Option C. Okay, so let us move to our next problem. So there is a, it's similar to the previous problem, and it is asking you to find out what will be the total charge on the triangle. Given that, so the triangle is not given here. Let me draw it. There is a triangle. This is 1, this is 2, this is 1, this is 3. So for this triangle, it's given rho surface charge density is 6xy coulomb per meter square. And you need to find out the total charge. So solve it and let me know the answer. Let us say this is x, this is y. Well, you are quite close. The answer is 13 coulomb. Maybe some calculation mistake was there, but I think you followed the right steps. So you have x from 1 to 2, 6xy, dA is nothing but dx dy. And when x varies from 1 to 2, y will vary from 1 to. So you need to calculate the relation between x and y. So this will be minus 2x plus 5. And this will give 13 coulomb. Check it just. If you are having, if you are finding any other solution, then let me know in the next lab session. Okay. Now we'll solve our last problem. This one. It may seem quite trivial, but the answer most of you maybe you will get, you will follow the wrong step and you will get a wrong answer. Okay. So question is quite simple. There is a static charge distribution produces a radial electric field. It's given is A e to r minus br by r square r. A and b are constant. And it is asking to find out what is the charge density and what is the total charge Q. And as we have seen the same type of problem before also, so the step is to use divergence differential form of the Gauss law. So divergence of E is rho by epsilon naught. The mistake that you will make is, so when you take the divergence, you will directly write as 1 by r square dou by dou r square e to r minus br by r square. R square will cancel. Only this will give. You will take the differentiation of e to r minus br, then you will follow and will calculate rho, then q. But this is wrong. This is wrong because this r square will cancel with r square only when you are not considering the origin point. So when r is 0, then you can't cancel r square with r square. Okay, so that is why whenever there is a 1 by r square term, or just check whether the electric field that you are considering, whether it is giving any non-zero value of r. So if it is some r times e to r minus br by, let's say, e to r br, let's say only e to r br, then it's fine. It's considering the r equal to 0 term. But when you have, or let's say you have r square e to r, what I mean, er is given e to r minus br by r. So for this, r square by br r. So this is also fine because r is non-zero here, r is there. So it will consider the zeroth term also. But when it is 1 by r square, this r square will, it's hard to cancel r square with r square. Okay, so that is why what you need to do, you just need to follow the what is the formula for getting a divergence of two variable which are function of r. Okay, let us say you have two functions u, v, both are function of r. So this, if you see the what is that the book. So if you see the book, it's already derived. It is divergence of u dot v plus u divergence of v. Okay, so you have e as a e to r br by r square r cap. That means divergence of e. This will be a divergence of e to r minus br by r square r cap. So a gradient of e to r minus br r cap by r square. So I'm taking this is as u, this is as v. So you will see why I am taking this as a v. So now we have e to r br and u e to r br divergence of r cap by r square. And this term, this is Dirac delta function 4 pi del q r. This consider the origin also. So that is why I've taken rk by r square as v and e to r minus br as u. Now the steps are quite easy. This will give a minus b e to r minus br r square e to r minus br 4 pi del q r. Okay, so rho is minus a b epsilon naught or br by r square plus 4 pi epsilon naught a e to power not e to power minus br del q r. So you can see here there are two charge density. One is a positive charge density, which is at the origin, and the value is 4 pi epsilon naught a. And one is a radially decaying negative charge density. This one. So this will be the charge density expression. If you ignore this, the answer will get is this one, using the same procedure that we have used to follow. Okay, but you can see here this also have additional term, which is 4 pi epsilon naught a, and because of this term the total charge will be 0. Okay, check whether the total charge is 0 or not. If you are getting any doubts, then let me know in the next live session. So this will give 0. Okay, so is this problem clear? If yes, then we'll stop for now. Then start solving the next part of this electric field in our next lab session. So anyone has any doubt? Dinakar, do you have any doubt in this problem? Let me know, then otherwise we'll stop. Okay. So what I have done here is, so whenever in any type of electric field expression, if you see there is a RK by R square term, then in that case you need to be careful while calculating the divergence of this electric field. Okay, because RK by R square, it will give a delta term. So that is why instead of, so if you recall, if you want to find out the divergence of E for any type of electric field, so what you do? The formula is 1 by R square, dou by dou R of R square and ER. And because this field is R square term, this R square will cancel. What you will get is 1 by R square minus B e to power minus B. But this is wrong. This is only half part of the solution. You can see here, this is the half part of this charge density. The other part is the origin. So that is why what I have done. So you need to follow this formula. So you have a variable, you have a electric field here, and it has two functions. One is e to power br and one is rk by r square. These are function of r. So when you have two functions, you can follow this formula. Okay, this is divergence gradient of u dot v plus u divergence of v. So now in the next step, what I have done, I have taken u as e to power minus br and v as rk by r square, so that I can get the delta term. So that is why I have taken v. V is rk by r square. You can see here divergence of rk by r square will give 4 pi by 4 pi del qr. So next what I have done is just substitute u and v. So this is gradient of e to power minus br dot rk by r square, and this is u times divergence of rk by r square. The second term is straightforward. This is 4 pi del qr, which is written here, and this is e to power minus br. And for the first term, divergence of e to power minus br, it will give minus b e to power minus br r cube, right? So this is what I have written here. Minus b it were minus br by r square. So you have already calculated it. So rho is nothing but the summation of this term with this one. So there is a charge density here at the origin, which is 4 pi epsilon naught a at r equal to 0. And there is a radially varying charge density, which is minus a b epsilon naught e to power minus br by r. Okay. So this is how it's like for inverse square law, it's electric field is RK by R square. So for inverse square law, whenever you have a electric field expression in terms of inverse square law, then you can follow these steps. Whenever you are seeing the electric field as RK by R square term, so follow this step. Don't follow the direct formulation of the divergence. Okay, that will give only the first part. The second part it will give as a 0, but it's not 0, right? Is this clear now? Okay. Okay. So then we'll stop now. So thank you for joining the session. I hope the problems will be helpful for you uh, to solve the assignment that has been released on the NPTEL site. We have one more problem to solve, but we'll see in the next live session. So let us meet on next Friday, same time from 6 to 8. Thank you for joining the session. So, goodbye, everyone.